Good morning, everybody. My name is Pablo Antonin. I'm from the Fraunhofer Institute. He is an Institute for Experimental Software Engineering in Kaiserslautern, Germany. And one of the areas that we've been working in the department that I lead on embedded software engineering is on, it's really loud this here. Can you turn a little bit down? Thank you. It's on continuous software engineering, right? So there is this trend going on, and the challenge that we have these days is how to integrate that with the development of embedded systems. And basically, what I'm going to present here is let's say, the first promising results that we have collected in the last, let's say, 1.5 years. This work has been developed together with the University of São Paulo in Brazil, with Elisa Nakagawa, and with this company called Ergozyne. This is also in Germany. What motivates us to do this work on continuous software engineering and embedded systems? So the world is dynamic, and that's not only true for information systems, for apps that we download in our mobile phones, or for information systems that we see running on a website and so on. The world is becoming dynamic also in the embedded world. What I'm talking about is exactly this. So BMW is working on the engineering of their autonomous cars. And they are working with an engineering cycle of 14 days cadence. This means whenever some kind of failure or bug is detected in a car in the field, so they have 14 days to get the data from the car, repair that bug, and deploy the solution in the vehicle. So this, for the automotive industry, this is unbelievably fast. So we're talking about things here that happened in the past like half a year to solve stuff like this. And we are talking here not only about failures in your infotainment systems. I'm talking about failures in your powertrain. Safety critical functionalities that has been identified, fixed, and deployed in 14 days. So there are companies, so for BMW, we don't know too much what's going on. So there are some guys that they give some speech in some conferences, industry conferences, and there are some white papers describing stuff like this. Tesla has provided more information on what are the challenges that they are doing, that they're having, how they're solving that. And that's somehow where continuous engineering is starting to take place in the development of embedded systems. Well, we know that what Tesla produces is basically, they have a software-defined car. So whenever you buy a Tesla, there are already controllers embedded in your car that they have basically very few functionalities running on it. And the idea from Elon Musk, and he already made it public, that is that he would like to have the car ready whenever he has some crazy idea to deploy it in the vehicle. So the hardware is already there. What are the guarantees that the software will comply to the hardware? And that's where the guys started to do their engineering stories. So there is a very interesting post from Elon Musk on how they make this thing so dynamic. Let me show an example. So what Tesla basically does, they're continuously monitoring social networks or even systems that they can feed to get user feedback. And one of them is the CEO of Tesla, the Elon Musk. So I don't know if you already read, but he make explicit that he keeps reading tweets and answering tweets from until, I don't know, 2 a.m. in the morning, and he really fights on the Twitter, in the social networks. There is one case where one guy said in his Twitter, hey, Elon Musk, it would be great if I could have a feature in my Tesla that whenever I stop my car, the seat would go back and the steering would go up. So you see that he asked it on 19th of August of 2017, and this very same on the very same 19th of August at 2:11 a.m., Elon Musk responded, good point, we will add that to all cars in one upcoming software release. So are you realizing what's going on? This guy is talking, he's making commitments on the steering system of the car in his Twitter on the same day. Well, there are two things that might have happened here. So one, he is so sure that his product is stable and robust enough to support that, or he was inconsequent. I don't know, I'm not here to judge him, but the thing is that he promised, and on November of 17, the feature was released in every single Tesla. Over-the-air software update. This is continuous engineering. So we are talking about features and processes that are coming, continuously being modified in the system. If you look for the definition of continuous engineering, you will find some of them, and IBM is kind of has a strong opinions on here and is leading the decision, so to say. So it states that continuous engineering is about one, unlocking engineering knowledge from different disciplines, continuous verifying the adequacy of the features that are being implemented with respect to service delivery and the degree of quality, and of course to always make use of strategic reuse. So this whole idea of product line engineering, product line architecture coming back and following this decision. Do you know what's very interesting is that the community on continuous engineering, let's say the scientific community, is not that strong. I don't know if you had the curiosity to search for continuous engineering conferences. There are very few. There is one ICSE workshop that deals with it, and mostly they are industrial conferences. So, and as I said, IBM is leading that. And what they have here in this picture, you can see an overview on how they perceive, and together with some individuals from this guy Fitzgerald and Stoll, so they published this paper in a journal that's very interesting. Here you see how we go, and the picture is really bad, I'm sorry for that. It goes from the business to the product development in the operation. So meaning, what we're seeing here is that whenever you're driving your car, I'm gonna focus on the car because I gave two examples from the automotive domain. Whenever you're driving your car, there are sensors that are continuously monitoring what's going on. And also that has to do with user satisfaction. It's not only how reliable your car is and how the software is executing that. And then there is the cycle. How would these repairs should be performed? How long should it take to enable that the business of my organization will follow up? And then I have to plan the development strategy to deliver that. How do we still engineer embedded systems? We are talking about continuous engineering. We are talking about delivering features within 14 days. But how do we still do these days? We are still really focused on the traditional V model, right? We start on the architecture drivers or the requirements, and then we drill down to the software architecture, system architecture, and whatever name you want to call that at the design level of the system. We go through the implementation, and then we go verification and validation. Of course, we are also doing model-driven testing where we execute tests at the design level. However, the techniques that we have, they are still not there to be implemented in the context that we are talking here, to have to be right away, to have the features verified right away. Another thing that we do, of course, we are focused on view-based architecture specification. And in the embedded systems domain, this is really a must. You have to have it. If you go, for instance, for the medical device domain, you have really to specify in the certification document that you will submit what are the safety critical functions. You have to specify what are the architectural elements that compose it, and they have to be in a separate documentation, a separate part of that document. But we still focus on architecture views. They really have to specify the context that the system is going to run, the functions, how they iterate to each other, software entities, hardware, and so on. And then we have, of course, the source code that's going to be deployed to the hardware. So it seems that we are still in a very traditional way of doing that. There's nothing wrong on doing that way, but we have to find means to be more dynamic, to enable this agility that has been placed and demanded by continuous software engineering. And if we think on the challenges that are to come, I really have seen in our customers a motivation and a really, let's say, an attitude to change the mindset, to keep using stuff like this, but how to adapt that for new classes of system like autonomous cars. So this is an Audi A7 released in December of last year, and they have already assistant traffic jams parking pilot level 2 that can park your car. So not only for let's say cars that goes until 3.5 tons, but also heavy trucks with autonomous truck doing platooning. We have autonomous mining. We have like, this here is a very interesting in the smart agriculture. So this is a cucumber harvesting machine that it harvests cucumber. It has been developed by a Fraunhofer Institute in Berlin. Well, are we really ready to cope with all this complexity of the systems and with all these dynamics that has been imposed? So we have to find means to integrate that whole thing. I know this was a long introduction to tell the problem what's going on, but I think that it's important to discuss that and to give this briefing to you guys. Whenever we were investigating, when we started our research on continuous engineering, I came to this phrase. To get the biggest bang of your modeling buck, you design your models to be executable so that you can run simulations to test your design against requirements before actually building your system or even prototyping it. When I came to the simulation word, I came to this challenge here. This is called the evaluation challenge that has been discussed by the autonomous driving community. To test all the features at the architectural level of an autonomous car, the car has to drive 88 times the distance between the Earth and the Sun. How am I going to do that with the car running? We have to go to simulations. We have to go to virtual prototypes, and BMW is going that. 95% of the architecture evaluation has to be virtual or simulated. So we have to find means to run simulations within our architecture models. We used to say that we build models that will target different stakeholders to communicate with the developers, to communicate with the business level, to communicate the features to certification authorities. But we have also now, with this new context, to build architecture models to enable simulations at the model level. And I'm talking about hardware-in-the-loop simulation, model-in-the-loop, software-in-the-loop simulations. There are simulators already in the market that enables you to do that. For instance, if you go to MATLAB Simulink, where you can really specify functional and logical models, or there are other solutions such as the one deploying here. The thing is that to build such a simulation models, you have to go really deep. You have almost to implement a variation of the source code that will execute the system in some things like these are virtual prototypes. And then you're deploying something called hardware in the loop. And that's when we said, okay, we need something in the middle. And that's what we call this V-Hill and R-Hill. They are basically virtual hardware in the loop and requirements in the loop. The requirements in the loop, they should be simulation models that they should be attached and related to the architecture drivers, functional requirements, non-functional requirements, the technical, organizational, and legal constraints, and the business goals. This is how we picture how these requirements in the loop should look like. And the virtual hardware in the loop, there should be something that you should be able to deploy your source code in a virtual hardware entity. So imagine the following. So do you know that's very expensive to deploy a source code in a hardware that doesn't exist or that is too expensive to test? So you might have guesses. So I'm gonna maybe this controller is gonna be adequate to run my solution. But then I have to spend, I don't know, 150,000 euros to buy a version of this controller with the possibility of having it failed. Maybe it's not gonna work. One way to make it happen is exactly with this virtual hardware in the loop, is that you are able to really specify and create a virtual version of the hardware. We have done already experiments in the context of this work that we specified the virtual hardware for a memory. And we could see really in these simulations the heat of the processor, the heat of the memory, how it goes depending on the functionality that we were executing. And with that, we can come to decisions to say, okay, maybe this hardware is not adequate to run this piece of software. So one way that we have specified that, we have to have a dedicated specification of drivers and architecture decisions. The picture is really bad. I didn't know it would in my laptop look better. But what we claim is that we have to come up to a systematic way of specifying the drivers that can be somehow translated into simulation models. So if you go here on your left-hand side to the detailed specification of the drivers in terms of environment, the stimulus response, and response measure, you have to specify your architecture decision in a way that can be machine readable. So here we put the solution steps, in this case for a vehicle CAN bus, where we could say which communication goes from controller A to controller B through a vehicle CAN, in this case to handle security. So in this case, we can really generate stuff like this. From the virtual hardware that it can look like the source code on the left-hand side or this one here. So we are translating from this side directly to this one. We have automations in between that enable this translation and the verification to check if the quality properties and the service to be delivered, they really hold. One drawback that we have observed is that for each one of the virtual prototype, we really have to implement something like this. And that takes a lot of time, and we need a lot of expertise in individuals with knowledge in the language that we are specifying the virtual hardware. So in this case, we have something in-house. Let's see, in the Fraunhofer is our platform, is a simulator. It's called FERAL. It stands for Framework for Simulator Coupling on Requirements and Architecture level. And we have really implemented different hardwares in the virtual level. So these are basically the entities that we have implemented, and we can directly focus and point deploying software or deploying the source code to execute into these entities here. We have also observed that when it comes to the source code, that the gap that we always see between the architecture and the code implementation that we always see. So of course there are platforms and tools to do that, but this model in the loop and software in the loop, they are somehow into these iterations, they enable us to somehow close this gap. And what I already said, so when it comes here to the implementation, instead of going directly to the hardware, I can somehow go into this virtual hardware in the loop. So this whole process here becomes more dynamic because I'm dealing with virtual models, and I can directly make changes. And just when I'm really sure on what's the appropriate architecture decision and solution, we move on to the concrete solution and the concrete hardware. This also made us to think, okay, so we have to somehow rethink this V model that we are working on. So we took this notion of the shift left or front loading, and we made it, let's say, we put parallel the two legs of the V. And then we call it this II. And then we say that we should go from the specification and design and the integration and testing, they should run in parallel, being supported by the simulation models. And then in each one of this level here, I can continuously check what is going to happen at the requirements level, if the requirements they are consistent and complete. And when I go here to my model in the loop, I can check here my requirements are against my architecture design and my architecture models. And then I can integrate directly the software. And then continuously I'm building and I'm continuously checking. And then I can deliver with more certainty in here. So these ideas of having virtual hardware in the loop and having this II model, this old concept, we somehow implemented it in the context of this company. And we basically set up a Git structure followed by a development process where we go here on the very left-hand side to the requirements. And then we have these executable requirements, which I specified in ways like this. And then these executable requirements that might directly check if there are violations or not. And then from here, we can directly generate code. And all these steps, like build for the virtual hardware in the loop, the hardware in the loop, the deployment and the monitoring, they are automated in a pipeline step. So we still have the challenge that we have observed that is expensive to implement this virtual hardware in the loop. We saw that there is a value for that. We saw that the benefit that it brought it here that we could test different solutions with with an improvement on the timing. However, it still demands time to implement this kind of virtual prototypes. It really demands time. And that's why we are somehow working now in some kind of domain-specific language where we could really specify these virtual prototypes in a less codey way, that we could somehow have some kind of models, and then we can specify some constraints for the virtual hardware in the loop, but not have to specify completely by code. And that's something that we believe that should be one of the steps to go from now on. And of course, whenever we do that, we have to understand how the other virtual prototypes, they are being bound together, so we could put these guys and create an integrated model. So to do that, to close this, we are also experiencing this here. After the success that we had in this company, we are bringing this to this Industry 4.0 projects. We have a front in our institute that's working on that. And in the Industry 4.0, there is a very strong concept on digital twins. So we already saw this today, and there is this digital representation of the real world, right? And our idea is that we could build some kind of simulation model, virtual prototype, that we can really go. In this case here, we're going to have the physical world running, but we create a digital world with these virtual prototypes that we can really specify and simulate properties and take decisions at the virtual world and just deploy to the real world whenever we are sure about the decision that is supposed to be taken. So these are somehow the steps that we are working on. So I would say that the concept, this concept of having the integration of requirements in the loop and virtual hardware in the loop, within the integrated way of seeing the V model in two consecutive ways. The concept is, the proof of concept is there, the implementation is there, but the challenges are still facing, but we are working in that. Thanks for your time.
Thank you very much for this nice talk and also for mentioning Palladio. We will pay the money for that later.
You're welcome.
So what I was wondering when you talked about your virtual hardware modeling language and also in the more general context of the digital twin, when you define such a language, you always make an abstraction, obviously. When modeling, you do abstractions, you omit details. And usually your abstraction is, let's say, oriented towards the analysis you later on want to do. And so what I was wondering in your talk, and also later on the more general digital twin question, how specific later on is your question towards the analysis, or how generic can it be that you say, I have my language for the virtual hardware, independent of the analysis I want to run on it. And what is your experience with that one? So how specific is your language for the analysis?
Yeah, what we have observed is the following. So the challenges, or the challenges that we are somehow specify at this, let's say, in the planning phase, I'm going to call the planning phase at design level that you say, we are really trying to stick to the certification process that the domain is constrained. Because then, because it's too expensive to do that for all the features in one system, right? So we have to really see a challenge to implement. We really have to see a challenge to implement something like this, right? We say, to which feature should I do that? Do that for every feature in your car that if it fails, it might lead to a death of someone or a crazy accident. So, for instance, for these vehicles that goes until 3.5 tons, we say, okay, we limit ourselves to the constraints or to the properties of the ISO 26262. If we go, for instance, for heavy machines that englobes the agriculture, constructions, and so on, and then we have a modeling language that constrains for this specific domain, it would be really unrealistic to say that we can model every single aspect to do predictions. But what we try to do, just to close, is really to bind them to each one of the domains. You're welcome. this one you mean, the requirements in the loop? Yeah. Yeah, which kind of abstraction we specify that? Yeah, so in the automotive domain, what these guys are doing, they're really specifying things with a controlled natural languages. So we do not stick ourselves to really informal specification or natural text, but these guys are not also bind to, for instance, a sequence diagram where I specify what the system should do. So what we have observed is a tendency to have this controlled natural language. And the good thing about this is that I can do a easy translation to a natural language, but also to a more formal model. Then we have something here in between.
Okay, and how do you simulate it? So are you translating?
We translate that, we transform that in more formal models,
And then
and then we run the simulation. Exactly. For instance, here what we do, we have really a system that is running in the back that interprets what is there, for instance, for the controlled natural language. And then we check the properties that the guy is supposed to specify in the boilerplates. Basically, this is how it goes. And then we can go from the requirements and simulate according to the requirements what is there to check how realistic that is, without the need to have a detailed architecture specification in the middle. And then already here, I can perform already some initial simulations. And here I can already make some cuts and say, this requirements here is not realistic because the design will not support it, or the domain will not support it. And then we go one step further, and when we include, for instance, the model in the loop simulations, we say, okay, even that the requirement is needed by the domain, is not really realized by the architecture. Yeah.
okay, so
Thank you. Thank you.